All right. Hello, everyone. Thank you for tuning in to today's Corundum developer meeting. So let me go ahead and kick this meeting off with the agenda. We got a couple of quick announcements. Then I got a few status updates. And then we got a special presentation on um, integrating some logic with Corundum called, I believe, pspin, pspin. Okay, one or the other. We'll hear more on that in a few minutes. Should be interesting. All right, let's see. So announcements. Just like to put the dates up here. The next Corona developer meeting will be on June 19th in 2 weeks, and the next Switch development meeting will be on June 12th in a week from today. So hope to see everyone there who's interested. All right. So status updates. Two main things for today. We got the PCI Express RX buffer management that I've been working on for a little while, and then I also have some updates in terms of Zinc device support, which I've been working on, over the past few days. So let's go ahead and get into it. Okay, so the PCIe RX buffer management has to do with the DMA engine and the PCI Express interface. And basically, PCI Express endpoints must advertise infinite completion credits, and this is to prevent deadlocks. Um, if you advertise infinite completion credits, then all of the traffic can drain out, and you're not going to end up in a deadlock situation in a PCI Express system. So that's a rather important um, aspect. But PCI Express interface cores usually have to do some amount of buffering on RX. So traffic that's coming in over the link, it's got to be stored temporarily. Um, Without the ability to apply back pressure for completions, it means that you now have the possibility of overrunning this RX buffer. You can exert back pressure against the other types of requests, right? The posted and non-posted requests, but you can't do that for completions. And one of the reasons we can get away with that is because the completion is always going to come in response to read requests. So what we can do is manage the outstanding read requests to prevent the buffer overflow of the RX completion buffer. So previously the Corundum DMA engine didn't do that. I think I was able to get away from that or get away with that because the Xilinx PCI Express IP core did a bit of buffer management itself and would prevent read requests from being transmitted if there wasn't, buffer space reserved effectively for those. But it seems that the code that does that, in the hard IP core is not perfect, and occasionally you do get buffer overflows. So I think some of the hard IP core bugs that I found may actually just be completion buffer overflows. Although I think there is maybe something weird about how the the overflows are handled by the core that's potentially problematic. But really, the solution here is to implement this properly in the DMA engine to prevent that from happening. So this is what I've been working on over the past few days to get this sorted out. And it's been kind of interesting, to say the least. Okay, so the management for this is, the mechanism is relatively straightforward. What we need to do is assume that the PCI Express IP core can store some number of completion headers and some amount of payload data. And then we're going to track the number of completions and the amount of data for every read request and basically consume those, those credits up to the limits that the core supports, and then release those credits once the operation is complete. Part of the problem, though, is that read requests can be split on the other end. So we don't know exactly how many completion packets we're going to get for every read request. So we have to assume the worst case. And in PCI Express, read data can be split on something called the read completion boundary, which is it's address boundaries of a particular granularity. So for endpoints, they have to split on 128 byte boundaries only. For the root complex, they can split on either 64 or 128 bytes. So worst case is one completion for every 64 bytes of read data. So that means for example, a 512 byte read request could potentially result in 9 completions, depending on the alignment, because these aren't, every 64 bytes of payload data, it's every 64 bytes of address space. So yeah, if you don't have enough header credits, you're going to run into the header credit limit long before you run into the data limit, which is potentially problematic if things are designed correctly. So taking a look at kind of the main FPGAs that are supported by Corundum right now, this is what the documentation has to say about the buffer sizes for Stratix 10, L tile, and H tile. They have 770 header credits, 2,500 data credits. That's pretty reasonable. You get 3.25 data credits per header credit, or about 52 bytes per header, which that's perfectly reasonable, because if you're running in a situation where you have kind of a mix of large and small operations, you're going to run into the data credit first, which that's fine, because that's still quite a bit of outstanding data, and you can get a pretty good throughput with that. For the P tile, the number's a little different. You have a few more completion header credits and a few more data credits. It works out to about 2.5 data credits per header credit, or about 40 bytes per header credit, which that's even better. For Vertex 7, Ultrascale, and Ultrascale Plus, the numbers are a little bit different, shall we say. For 7 series and Ultrascale, it's 64 headers and 15,872 bytes. The table says everything is in units of flow control credits, but apparently this is in bytes, which is odd. For Ultrascale Plus, it's 128 completion headers and 32,768 bytes. And these work out to have a lot more data for each header, which is problematic, because this means you're going to hit the header credit first and then get terrible throughput. So the Intel figures look reasonable, but the Xilinx figures, they don't make a lot of sense. So the question becomes, how does it actually work on the Xilinx devices? And I've been trying to figure this out. I have a post on the Xilinx forums asking about it. We'll see if I hear anything there. So if I don't hear anything there, then I guess I'm going to have to see if I can, manually reverse engineer this thing and figure out what the heck's actually going on. So, like I said, the manual, PG213 Appendix B, has details on what you're supposed to do to manage the completion buffer size. And they list the completion buffer size as 128 CPH and 32,768 B CPD, with the notation that the numbers in the table are in units of credits, flow control credits, where one credit is 16 bytes, or one TLP header. So since they have the data credit number in bytes, that's a bit of a head scratcher. And if you run the numbers with RCP 128, having 128 header credits means that only gives you 16,384 bytes worth of data to play with. So you can only use half of the data buffer if you have only 128 headers to play around with. If RCP 64, that's 8K of data. So that ends up significantly limiting the throughput. So what gives? Is this like a design problem with the PCI Express IP core, or is this a documentation problem where the documentation is given the wrong information? It seems like this is probably a documentation problem, and that the one of these numbers is wrong, or something about the details in the documentation are probably not correct. So what I've been trying to do is independently verify exactly what these cores are doing in terms of managing the buffer. So a few observations so far. The first one that's interesting is that the Vertex 7 core manual actually has different header credit counts in different versions. So like version 2 of the manual has 32 completion header credits, and version 4 point something has 64. So ostensibly the core is the same, because that's burned into silicon on the FPGA. So I'm not sure why they'd be presenting a different number, unless that there's some dependence on the soft logic, or maybe this number is, kind of misleading and not actually representative of, reality. um, Another thing is that the core uses external BRAM for storing the actual completions. So on UltraScale Plus, it's kind of a weird configuration. It consists of basically two parallel memories, each one with two banks, and each bank is 512 or each bank is 256 by 140, or no, 512 by 144. Yeah. So 512 entries, 144 bits wide. Um, so that results in 32 kilobytes plus parity bits, which that kind of squares with the 32,768 bytes in the table. But another thing that I noticed is that whenever I had isolated one of these, hard IP core bugs, basically, with the ILA, I was seeing garbage completion headers, right? So instead of like a duplicated header or a dropped header or something like that, I was seeing, garbage. So none of the fields made any sense, right? Like the completion status would be some weird value that was not allowed as per the spec. The completer and requester IDs would be, garbage, not corresponding to any device in the system. So you would expect to see that only if, the completion header was overwritten with data, as opposed to a header being overwritten with a different header. So that implies that these things are probably stored in the same memory. And I was actually able to verify this with the ILA, because since the core interfaces with these separate block RAMs, then what you can do is stick an ILA on it and verify that, yeah, we actually can see the completion headers getting stored alongside the completions. So we take a look at this Xilinx PCIe IP core on the Kintex, on a Kintex UltraScale Plus part, probing the completion RAM connections here with the read address, write address, read data, write data, all of that. We can see the completion header is being written into the memory alongside the RAM. And interestingly enough, this header is also in the normal, PCIe layout and not in Xilinx's, rewritten, reorganized header format. So yeah, but you can see the 4A here means completion with data, and then we've got, the A600 corresponding to the requester ID, so this is definitely a completion header here. So that means a few things. One of them is that using 32,768 bytes corresponding to 2048 completion data credits is wrong, because if you actually use all those data credits, you're going to overflow the buffer because all the completion headers also go into the buffer. And it's also unclear where that 128 completion header credit count is coming from in the documentation. So yeah, the two methods I think of for how to manage kind of this type of buffer correctly, I think there's two different potential approaches for that. One of them is to basically partition the buffer. And I put partition in quotes because they're not exactly like dividing the buffer into two pieces. We're just going to create two different credit numbers that add up to the buffer size. And then as long as we make sure to not violate either of these two values, you're not going to be able to have a buffer overflow. So we need approximately a 4-to-1 ratio, so we can actually get 64 bytes of data per header credit. So that ends up being something like 416 header credits and 1632 data credits. And you can fudge these numbers a little bit as long as the sum of them is less than 2048, or is less than or equal to 2048. Now, the second method is basically just keeping track of a single credit type. Maybe buffer credits could be a way to think about it. Basically, you add the header and data credits together for each request and then track that. And this, prevents problems with overflow, because now you are taking all of those headers into consideration. But the question here is there a limit on the number of completions that can be stored in the buffer? Documentation lists 128. Is it possible the IP core itself, the hard core, can only track 128 completions in the buffer, or can it actually track more? Not sure. I need to do some experiments to see if I can determine what number it can track. Um, Hopefully I'll be able to get this sorted out soon, and then we'll have all this implemented for all the different devices. So anyway, to summarize all of this so far, I've implemented the credit tracking in the DMA engine, basically the packet FC method in PG213. The methods in there actually seem perfectly fine. It's just the number of header and data credits you have to play with that don't make sense. So with this, there are two different parameters that are now specified for the core. You can plug in the number of completion header credits available in the buffer and the number of completion data credits available, and then the core will appropriately rate limit its outgoing requests to make sure that it doesn't overrun those values. I also connected the RCB status signals so the core knows what the configured RCB setting is. So if it's set to 128, then it can consume fewer header credits internally. And for the HL and P tiles on the Intel devices, I've gone ahead and implemented that as per the documentation, the buffer sizes, and I haven't observed any performance penalty so far. Everything seems to be working. For UltraScale Plus, I did some testing with the numbers listed in the documentation, and the read DMA throughput drops from 112, 110 gigabits per second to around like 87 gigabits per second. It's a big drop, so that's not good. So what I ended up doing in the development branch is I've implemented it as 128 completion header credits and 2048 data credits, basically what the documentation says, but forced RCB 128 instead of RCB 64 until I can figure out what the correct settings should be. And there is still apparently some performance penalty here since we can only use half the buffer size. So that's less than ideal, but hopefully I'll be able to figure out what settings should be used long term, and I'll get that updated hopefully this week. Maybe it'll take longer, but we'll see. I've been brainstorming ways of verifying the correctness of the buffer management, just so I can make sure that yes, this is in fact working correctly on both the Intel devices and the Xilinx devices, ideally. The problem is that it's pretty easy to hit the data limit, right? Because the buffer sizes are only like 20 kilobytes, 30 kilobytes, something like that. But hitting the header credit limit is more problematic because we only have 256 tags to play with. So if you take something like the Intel Stratix 10 core with 770 header credits, well, if I issue 256 small reads, that only uses 256 tags. If you issue 256 larger reads, well, then you're dealing with, how is the upstream, how is the root complex going to split all the requests? It's probably going to split them, with much larger than 64 byte TLPs. So you're not going to use, I mean, you potentially will use more, but you're not going to use all 770. So I've been trying to figure, okay, how are we going to, either get control over the root complex and get it to split stuff on a smaller granularity, or, is there some other tool that can be used to verify that? I was thinking simulation could be an option, and I actually tried running the test bench for the Xilinx PCI Express hard IP core, but I'm just going to say that test bench leaves a few things to be desired. I think their testing only does single D word reads, so it doesn't look like the infrastructure is there in kind of their root complex BFM to actually generate multiple completions for a single read request. That's problem number one. Problem number two, it's terribly, terribly slow. Yeah, so I'm not sure what makes the most sense there. And also that would only apply to Xilinx devices. I wouldn't be able to, modify the Xilinx test benches to test the Intel IP cores. So if we can find a way to do this in hardware, that would be great, but haven't sorted that out yet. So hopefully I'll be able to make some headway on determining the buffer sizes for Xilinx devices, at least this week. Right. So that about wraps up the PCI Express buffer management stuff and the significant head scratcher that's been. And I'm going to talk about the last bit of status that that I have to report on for the past couple of weeks, which is Zinc device support. So Xilinx sent me a KR260, a Korea KR260 SOM. So I've been working to try to get Corundum running on that thing. The problem with this particular SOM is that it has kind of its own built-in bootloader setup. The FSBL is, burned into, I'm not sure if it's QSPI flash or eMMC or what, but it has that already baked in. Unlike like the ZC102 and ZC106, where it'll load the FSBL off of compact flash card. So I'm actually not sure the proper procedure for dealing with Patalytics on this thing, and Patalytics is just kind of a pain in the butt. So what I ended up doing is saying, okay, I'm going to take a step back and see if I can get this thing working with Ubuntu, because Xilinx has Ubuntu images for these boards anyway. You can get one for the Korea SOMs, and you can get one for the ZC102, ZC106, and that image might actually run on a few other boards too. I'm not sure off the top of my head. But the main thing that you need to figure out for that is the device tree, right? It's one thing to have the FPGA config that you can load through the operating system once it's booted, but then in order to load a driver, you need the device tree. So it took quite a bit of head banging to figure that one out because it's very poorly documented. But I was able to finally piece together everything that needed to be done for the device tree overlay, and it ends up being a much simpler process than the Patalytics build, because basically you just need the bit file, but convert it to a bin, and the device tree, and then like just a fixed JSON file, and then you just copy that over into like libfirmware Xilinx on the board, and then you just use xmutil load app, and it loads both the device tree and the FPGA image. So this works on the ZC102 and ZC106. The hooks for that have already been added to the upstream, or to my development repo. There are still a couple of issues to sort out here. There seems to be some sort of reset sequencing issue on the 102 and the 106, also related to the clocking, because the clocking only gets updated when the driver is loaded. So that means by default, one of the reference oscillators will run at the wrong frequency, so that'll get updated when the driver is loaded. But then the transceivers have to be reset, and the PLLs and whatnot, for all that to figure itself out. And even after adding support for asserting the reset, that doesn't seem to work reliably. So at some point, might need to sit down and figure out what needs to be done such that you don't have to like load the driver, unload the driver, remove the FPGA configuration, reload the FPGA configuration, reload the driver, just so the link actually works. So that's a potential problem. The other problem that I ran into is that it doesn't seem to be loading the MAC address from the EEPROM on the ZC102 and the ZC106. It wasn't clear why, because you could read the EEPROM, but the calls to go through the NVMem subsystem to read the MAC address are failing. So I don't know why. I don't have time to go diving into the NVMem subsystem to try and figure out what is breaking there. But yeah, that's I'm gonna boot that one down the road a little bit and work on other things. But yeah, the big thing is that I was able to get it working on those boards, and then I also went ahead and got it working on the KR260 as well. I didn't add Patalinux support for that because it's kind of a pain to deal with Patalinux, but it does work just fine under Ubuntu, just like on the ZC102 and ZC106. So all of those devices now work. And I also went ahead and added some support to the driver for asserting the reset line, because that's apparently something that they've added a whole subsystem for. So you can just add a couple lines to the device tree indicating where the reset line is located, and then a couple lines to the driver to toggle the reset line when the driver is loaded, and everything works. So that definitely helps get everything working on the KR260. And unfortunately, it doesn't seem like quite enough to get everything working on the ZC102 and ZC106 because there's still some sort of a reset sequencing issue, but it definitely helps. So that change has been made in my development repo as well. So once I get some of these other kinks worked out, then hopefully that'll end up back in the main repository soon. All right, so that about rounds off all the status updates that I have for this week. If you have any quick questions or comments, I'll go ahead and take those. If not, then I'm going to turn it over to Peng Chung, who has a presentation on pspin. No questions or comments? All right, sounds good. I'll go ahead and turn this over to Peng Chung.
All right, cool. Thanks, Alex, for the status update and a quick introduction for my part. And let me just go ahead and share the screen. Yes, should be.
There we go.
Yes, and I need to. Oh, Zoom pop-up is covering the PowerPoint toolbar, which is like, yeah. All right, you can see. Can you see the slides?
Looks good on my end.
Okay, nice. So, all right, everyone, welcome to my presentation on the pspin, or here we actually have another prefix, the fpspin. You'll quickly see why that is called fpspin. It's like we're just prepending more and more prefixes to this name. So the original name is spin. That is quite straightforward. And so the correct, like you did it correctly in terms of pspin. That's a P is how to say prefix. You'll see quickly why that is the case. And before starting, I'd like to say that part of the slide deck is of courtesy of the spin team. And just to say quickly, thanks to them. All right, and let's get started. Oh, okay, I think I have some quick animation issue. Let me just add it there so that I can properly show you the thing I want to. Yeah, let's do here. Okay, I hope this works. Oh no, just get away from here. Yeah, no worries, doesn't hurt the point. All right, so first I'd like to show you like what does the typical system look like with the bump in the wire smart NIC. I hope this is not too foreign a concept to most of the audience here, but just in case, we have so usually on a system we have a CPU that runs the kernel, operating system kernel, and user application. We also have a NIC on the side, apart from on the side of the CPU, that receives packets and forwards them to the CPU, right? And in the by bumping the wire smart NIC, what's different here is that apart from the usual NIC infrastructure that we see at the bottom part of on the right side, for example, we have the PHY, we have the MAC, we have the data path engines that does all kinds of offloading, but also all kinds of queue processing, and also the PCIe interface to the host. We also get a processing cluster that can do arbitrary types of processing on the packet before passing them onto the host, or even in some cases not passing them at all onto the host. So as a quick demonstration, we can see that so here we can have an interesting packet incoming from over the PHY, and then the packet will traverse the PHY, the MAC, arriving at the data path engine on the NIC side. And then what's different from a normal NIC operation point is that here we have this matching engine that tries to determine that if we want to take a look at this packet in the processing cluster inside the smart NIC, and if that is the case, that means this packet will be marked as okay, this will be processed at the smart NIC, and it will go over the scheduler and the DMA and the local DMA engine to go into the local memory inside the processing cluster, and then the scheduler will select one core to take a look at this packet, and then this core can then further decide on that okay, I'm finished processing this packet and just finish, or I can also decide to forward this packet further to the host. So this will then go over the PCI interface, arriving at a dedicated buffer inside the host kernel for the user application to read afterwards. And this packet will then, on the request of the user application, the packet will then go into the userland memory for further processing. And then I got rid of the weird animation I just put in last minute, but the point is basically we have multiple vendors already implementing SmartNIC inside as part of their solution. So for example, Azure, they have their in-house SmartNIC, and also Xilinx and Mellanox are providing products for further integration. For example, Xilinx has this U25 SmartNIC, and then Mellanox also has their Bluefield, Bluefield 1 and Bluefield 2. There are different flavors of the SmartNIC, but I think specifically Bluefield 2 and 3 are the bump-in-the-wire style SmartNICs. And here, what about this pSpin thing that is in the title, right? So at ETH Zurich, the SPCL group, we proposed this paradigm called SPIN, which is streaming processing in network. And this, what this actually means is we have, this is basically a computational paradigm or model that we define here, that how we're trying to summarize how these bump-in-the-wire NICs are going to work, right? So this abstract machine model looks like the following. So here we have a compliant NIC that implements the protocol, and we're going to have some fast shared memory between all processing units on the NIC. And then this is going to be used as the packet input buffer. And then we have a packet scheduler that takes arriving packets and directs them to one of the many processing units that's available on the SmartNIC. And then there's also going to be a DMA unit that handles any kind of memory request the processing elements wants to make to the host memory. And then, yeah, this manifests as the host memory sitting on the other side of the DMA unit. And this DMA unit can then issue read or write requests to this memory. And the CPU then sits on top of this memory. Yes, it doesn't really matter what type of physical interface is there between the SmartNIC and the CPU, but for the sake of simplicity, we can assume that is PCIe, right? But there could be other exotic type of interconnect. And then what the CPU then does to the NIC is it can upload handlers, or that is our terminology for the packet processing routines that run on the SmartNIC, which means a packet arrives and then we handle the packet via one of these handlers. And then it also manages the memory, like how do we allocate this input buffer? How do we allocate the scratchpad memory that the packet processors use? And then here I have a little animation showing that, okay, we have packets arriving from the outside network. It goes over the packet scheduler, and then arrive in the fast shared memory. The HPUs are then going to take these per the request of the scheduler. After processing them for a while, they're going to be sent over by the DMA unit to the host memory for further inspection by the CPU. And then one important question here is, how is this paradigm different from RDMA, right? That is the remote DMA, as it's very common in data center network processing. And then we can take a quick look at this example of streaming ping pong, right? So for example, the streaming ping pong, the initiator is going to generate a string of packets that it sends to the target host for a simple reply back. And then in RDMA, what's going to happen is the initiator prepares the packet in the CPU, sends it to the NIC, and then the NIC sends it to the other side of the NIC, which is then going to do DMA into the host memory, or say the target memory. And then the CPU can then take a look at these incoming requests, this ping packets, and then it's going to send back RDMA response via the NIC to the remote host. And what is then different when we have spin in the picture, right? Because here we're looking at one rather simple operation that is just basically pawn the packet back. But on RDM, in RDMA, we still have to have the CPU take a look at this, actually handle this action, because there's no arbitrary processing power inside the NIC. We can't just tell the NIC to just send the packet back whenever you receive such a packet. So what spin is going to enable is the packets are going to arrive on the target NIC, and then the target NIC is just going to have this handler that says, whenever you receive such a packet, send it back. And then this packet is just going to directly be sent back by the NIC and doesn't even go inside the host memory. And by this, we can save quite a bit of latency on the whole data processing path. And in fact, per the regular application inside high-performance computing, for example, which is one use case of Spartan NIC, a lot of situations you don't even need the host to do any kind of complicated processing. You just need some simple forwarding. For example, if it's or reduce or scatter gather, this can already be sufficient. All right. And then where does p-spin, the p, come into the picture, right? So p-spin is then a pulp empowered implementation of spin. This in-net computing paradigm. Pulp is a CPU design led also by ETH Zurich at another lab. The main characteristics is it is an ultra low power platform and designed for IoT applications that has very low area and power requirements. So, but we can just look at it at the moment as a processing cluster that we can plug in for simple packet level processing. And then on the left, you can see that this is a very simplified simplified model of how a smart NIC is going to look like. So we have the network interface at the top, we have the host interface at the bottom, and then in the regular outbound and inbound engine, especially on the inbound engine path, we have the spin unit, p-spin unit that implements the spin machine model that we just talked about. It's going to look like looks like this. So first we have the 3 different types of SRAM buffer that is used for buffering incoming and outgoing packets, and then also holding the program, and also scratchpad for the handlers to execute upon. And then we have a scheduler for the packets. We have a number of clusters that sits on the NIC, and each cluster has then a bunch of cores, and then there's also the NIC level and the p-spin level, DMA engine and command unit, and also monitoring and control units. And then here comes the part that I actually actively worked upon, and here should be a very similar diagram to most of you. What I'm doing in this project is we are integrating spin, or say specifically p-spin, with a real-world NIC that functions in hardware, because so far what the p-spin effort only includes a Verilator-based simulator to verify that, okay, the hardware is working. We have a Verilog model that is tested in simulation to work, but we're not sure how it would actually interact with a real-world NIC. So in terms of Corundum, introduced this to the spin team as it's an open source 100 gigabits per second NIC for FPGAs from UC San Diego. And what is important here that we handle, that I actually worked on, is this application block inside the FPGA, but also the application interface for the software on the host. So we use Viado IPs and also basically AXI interface IPs, and then the p-spin Verilog implementation. And then on the host side, we also implement kernel modules and user space libraries to implement the spin computation model, computation paradigm. And then we're going to take a look quickly at the hardware side, how the hardware bridge blocks, I implemented a number of bridging IP blocks that bridge the interface of p-spin to Corundum, the interface Corundum provides. Let's take a look. Here's an overview. It's a very complicated diagram, but you don't have to remember all the details. So here, the gray block is an umbrella for everything that fits into the application block of Corundum, which is basically all my additions of all my hardware additions is going to sit. And then so as we know, the Ethernet packet data comes in from the interface module. We're using the interface module, which is the highest latency, but the single interface that aggregates data across all the possible port splits, but that's just technical detail. It comes into this ingress data path module that does a bunch of things, and then finally converts it to DMA requests into the NIC memory. Basic AXI write requests into the pSpin memory. Sorry, and then at the top we have a bunch of control path or / configuration interfaces for host access to the pSpin memory that we can load program into the cluster, and then we also have a set of control registers that basically acts as GPIO registers that we can pull the reset of the cluster, and also, for example, there is a fetch enable of the cores and all kinds of stuff like that. And yes, I just talked about the packet data path. So we have the ingress data path that we match if the packet is going to go to the cluster for processing. We then allocate the packet, the space for the packet inside the packet buffer. We do DMA into this pSpin memory, and then finally we generate a command for the scheduler to schedule one of the cores. And then for the egress DMA, it's very simple that we just take a NIC command and then generate DMA request to inject back into the interface module. And then finally, the last part, but also very important part, is the host memory data. That's what completes the spin computing paradigm, which is we need to bridge the host DMA interface from pSpin, which is an AXI, to the Corundum segmented DMA interface. And so these green blocks are the IP blocks, Verilog blocks that I wrote as hardware for this project. And everything here is implemented with like the simplest design possible. We have just a bunch of state machines and no in-flight, multiple in-flight requests anyhow, because we can always optimize afterwards, and now we just need a first demo version. And then we can zoom out back to this diagram to take a look at the software side and how I basically implemented the software. So on the right side, we see a rough diagram of how the user application at the top interacts with the kernel modules, and then eventually with the NIC on the hardware side. And then here we use a very simple, very common routine, like important routine, which is the host DMA. That means how the pSpin cluster is going to write to the host side, to the user application memory. So first of all, what happens first is the host application is going to call into the runtime to initialize the hardware, which then the runtime is going to configure the registers, which is exposed via sysfs. Yeah, this is a quick hack because I just put together a bunch of shell scripts to read and write the sysfs registers. And then it then calls into mmap into this device file that into the kernel module, the application kernel module, which is going to allocate the DMA buffer and then map it into user space. So at the moment, we just use coherent DMA mappings. But later on, we may want to use directional single-use DMA buffers to improve performance. And then the pSpin hardware is going to perform DMA. So a request is going to come in from the PSIE bar into this buffer that we set in place, and then the host application in the meantime is just going to busy poll this buffer to say if something has come in. We may want to add interrupt support, but it's polling at the moment. So it then calls this push pop request and push response to say that, okay, I handled this this request from the NIC, and we finish processing this packet, we can go back to step number 4 to that the pspin is going to do another DMA request. Okay, and then what works at the moment is this extended ping pong that this demo that I implemented to test that every part of the system is working. There's a lot of moving parts. So a UDP ping packet is going to come in over the interface, arriving at one of the cluster cores. The handler is then going to say, okay, let's DMA this to the host, arriving in the host DMA buffer. And then the user application is going to see this packet, modify the payload, and recalculate the IP checksum, IP header checksum. And then the core, the processing core on the NIC, the pspin core, is then going to see that, okay, this packet is finished. We DMA it from the host, and then swap the Ethernet, IP, and UDP addresses / port numbers, and then send it back out. So this end-to-end demo, we had it like a very crude latency measurement that we have. So we have a packet come in, go over the yes. So we use the VCU 1525 NIC FPGA that has 2 ports, and then we attach the cluster to one of the interfaces. The other side is left untouched as a bypass NIC. And then the bypass side, we're going to run netcat to send a UDP packet over. And then arriving at the processing cluster, the first test is that we just send this packet back directly. And the end-to-end latency is about 4 microseconds, which is far from ideal, but there's a lot of room for optimization there. And then we can also do the same thing, but have the cluster forward this to the host application, modify it, and then put this back. And it's about 4.5 milliseconds at the moment. And then finally, the roadmap of this project. So as a master thesis project, I have 6 months. I'm 3 months in, so we have about half the time left. And we're going to aim for optimizing more synthetic benchmarks, and also try to port some real-world workloads that's developed in-house inside the group. For example, there is this one use case called MPI data types, which is implemented in Spin. It does serialization and deserialization of MPI data types on the NIC entirely. And then we are also targeting a key value store that uses Spin to do offloading to take cycles off the CPU. And this will significantly, I anticipate that this will significantly improve the completeness of the implementation, but also improve reliability, because at the moment we have various bugs that sometimes cause soft lockups. But yes, that's a further issue to work on. And finally, I hope that this is going to we can not only improve documentation on Spin or pspin, but also some of the parts that, since I wrote code for the hardware, some documentation on Corundum itself. So for example, how DMA, how to actually interact with the segmented DMA interface or stuff like that. And that concludes the presentation. I'm open for questions. Thanks a lot.
Well, thanks for the presentation. That's really cool stuff that you've been working on.
Thank you.
If anybody has any questions, feel free to fire away.
Yes, I have a question. Thanks for the presentation, first of all. And is this code available, or it's open source, or it's private on your company?
So the code of the pspin implementation itself is already open source. It's it's open source since the publication of the paper already. But that one at the moment only includes the processing cluster itself, which is a Verilog model. It's synthesizable. We tested it. We pushed through, like in the paper, we pushed it through all the like ASIC backends. It targets like 22 nanometers and stuff like that. So the hardware, the core processing cluster is open source. And I also have a non-official version that I'm working on open source on my personal repo, but that is not ready. Like we don't consider that's released by the institute yet, but I'm pretty sure that that's going to be open sourced as well and cleaned up in open source after, at least after I finishing my project. I'll make sure that happens. Yes.
Okay, thank you. Because we are working on something on the app also, but more for the 5G domain. So it's very
Yes.
interesting what you're
Yes.
doing.
So basically, this is also one of the one of the base motivations of doing implementing this whole platform is because I mean, sure, there are also other SpartanNIC platforms on, like for example, for sale from Mellanox or from Xilinx, right? But that's there are still basically closed platforms, and it's a lot of the details are not really known. And by building something open and open but also high performance, we can always tweak it on our own, or whoever wants to use it can change it on their however they like.
Okay, thank you very much.
Yeah, thank you.
So about the cores that you have in here, those are RISC-V cores?
Yes. So let me.
And this is a custom core that you guys put together as part of this spin platform, or no, the P-spin platform?
Yes. So
The cores are from Pulp.
It is so Pulp is a project from ETH Zurich that, I mean, from the IIS lab, and they basically say that Pulp is an acronym for ultra low power, and then it's a very small area, like a core very small in area, and then it's a very like a basic core in terms of in order. I think it has 3 stages of pipelines or something. But then it also has a bunch of DSP extensions popped on it. For example, like compressed loop formats and some arithmetics on packed, I want to say fixed point data, fixed point data formats, and a bunch of other stuff. So for us, it's like the reason we picked this core is first of all, it's a collaboration between different institutes at ETH, but also that just we kind of one of the motivations is these packet processors don't really need to do very heavy calculation. It's mainly not for offloading computation. It's for lowering the latency. So we can get away with having a bunch of very small cores, and yes, and then RISC-V is just basically the go-to choice for building new cores. So yeah.
Gotcha. How many cores are you guys integrating?
So I have another slideshow that has a bit more performance and area data. So the P-spin implementation, it targeted 4 clusters on GF22 nanometers. So we have about 18.5 millimeters square millimeters of area.
It's more in terms of what you're doing on the FPGA. I mean, yeah,
okay,
on an
sure.
ASIC,
on the FPGA,
like, but
okay.
if you're running on an Ultra Scale Plus, that's probably a different story.
So on the Ultra Scale Plus, I don't have figures ready here, but on the Ultra Scale Plus, on the View 9P platform, we have about 55% of usage for 2 clusters. Here you see that it's
of 4 cores each?
Of 8 core each, so that's 16
16 cores.
Yes.
Okay, that's not bad. And what clock frequency are you running at? Is all this running at a 250 synchronous?
No. This is the current culprit, right? It's like it's running at 40. The reason of this is being that this is a core specific, like it's really tuned for ASIC. So
I see.
It doesn't have it doesn't have any kind of design for FPGAs, for example, pipelining, any kind of stuff like that. But given that it's relatively simple to swap out a core implementation. So one of the things we discussed internally is a thing we could do is we could make a very like FPGA tuned version of this cluster by putting in something, for example, like Rocket Chip or something like that's one of the FPGA enabled cores by UC Berkeley, and then they have like they can customize it the core such that it can run at way higher frequencies but still remain quite small.
Okay, so the idea is that instead of using the pulp cores you would use some other
Mhm.
core, basically. Okay.
Yes, yes. Yeah, but that's like
I guess
the reason
there's a
I'm
bunch of possibilities for that these days.
exactly.
But yeah,
exactly.
okay, gotcha.
The reason we're not doing that is simply time constraints, because for me it's a fairly standalone project that I have to finish within 6 months, but we can't just try and do everything. So that's going to be handled later by me or by some other people.
Gotcha. Okay.
Yeah. And also another point is that I'm not so sure about whether Corundum is if taping out is one of your concerns, right? I mean, so far it's definitely designed for FPGAs, obviously. But or otherwise we could also like what was in the picture was also we could find another NIC that or use Corundum itself to do tape out, and then claim that, okay, this actually works in ASIC as well. That's also part of the motivation project.
Yeah, so I mean, the trick with Corundum is that, at least from my point of view, having it on an FPGA and being able to, swap out the design on an as needed basis, and having that flexibility is kind of one of the main reasons for developing Corundum. You burn it into an ASIC, then you lose all of that. But I can see the the argument for spinning an ASIC with some of that stuff. So if that's something that you guys are interested in pursuing, that's certainly something that can be discussed in terms of if there's any modifications that would need to be made to Corundum to facilitate that. I know you got to do things like pull all the RAMs out and whatnot, which Corundum uses a lot of inferred RAMs, so that could require a lot of work to modify. But if that's something that there's significant interest in doing, then that's potentially something we can look at. The other thing too is that I tend to use FPGA interface IP, like the PCI Express IP core and the CMAC blocks and whatnot. And I don't have time to try to write any of those from scratch.
Of course.
It's like if you want to do an ASIC implementation, you can't use a Xilinx CMAC block for that. So I don't know, what that would look like.
Yeah, I mean, of course, right? It's like if VR or if anyone is going to do ASIC, right? They're going to have some sort of IP vendor, right? For example, so here we have Xilinx as the IP vendor, but also you could have a design where I forgot you could have
Synopsys.
Cadence, for example, or Synopsys. Yeah, any of the major IP vendors that can
Are those the same company now?
No,
so many acquisitions.
I'm not sure. Well, yes, but of course the Xilinx IPs are going to be out of the question, but we are going to have to integrate some other kind of IP stuff.
Right. Yeah.
But
I mean, I guess there's multiple vendors for a lot of this stuff. So
yeah. But also another point about this, it's like, so we're still mostly doing this on a research scale and not really trying to spin a product, right? So a lot of the claims we're going to make is going to be that how confident we are that, for example, we have a floor plan and almost ready design that's with half a year of backend engineering, it can go to the foundry. Then that's already a pretty strong claim for publishing a paper in research. And then if we're going to do a company, for example, that tries to do products from this, it's going to be, there's a lot of extra work is actually going to go in for really spinning the ship. Yeah, but what's important here is the numbers the performance numbers, for example, they're sensible in terms of scale. Yeah.
Right. Well, I guess another thing to think about is any modifications to Corundum that would potentially, facilitate this type of application, because, I've certainly tried to provide, a lot of interfaces to the application section that can be utilized, but, maybe there's interfaces that should be added. Like I know one thing that would probably make a lot of sense is to add the support for the application to generate events that can then be handled in a nicer way by the driver.
I mean, that's kind of one of the thing is, how does the application block raise the interrupt? That's
right. Yeah, right now I don't think there's a way to do that, but that's definitely something that that could be implemented. Some of the HDL for handling all the descriptors, completions, and events, I'm in the process of rewriting. But once, that is, as part of that, we can certainly look into supporting, more fancy stuff from the application block and whatnot. So, and
Yes.
I don't know if you've been tuning into the developer meetings, the recordings at all, or been attending these.
I've
but
been
I have
checking
been
out some
talking about-
slides actually, but not the
Right.
recording. Yeah.
Right, but I have been talking about some of the new descriptor management components and whatnot here and there, and that's partially to support better utilization of the PCI Express interface, but it can potentially also support more complex operations as defined by the descriptors. So I'm not
Yes.
sure necessarily how that would dovetail with something like pSpin. It's definitely more kind of for RDMA type stuff. That's kind of what I have in mind, but potentially there's you might be able to utilize some of those features in pSpin by passing per packet metadata on the transmit path or something. I mean, it seems like a lot of this stuff's going to be more useful on the receive path, right? Packet comes in and then pSpin has to match it and do something and get it back out the door, as opposed to on the transmit path. So maybe the event, having better connections to the event subsystem is going to be more useful than anything else. But that's definitely something that that we can discuss.
Yes,
I don't know if you have any thoughts on that now. We can certainly talk about it at a future date if
yes.
And also, now that you've been kind of working in the application section, there's probably things that you've bumped into that we could probably improve on, and be happy to hear about that.
Yeah, sure. I mean, so far I'm pretty happy with the infrastructure of like the kernel modules and stuff. But yes, of course, I mean, as I said just now as well, because I plan to integrate like this big thing that is the MPI data types. Like it's not a demo anymore; it's actually a real world use case, right? So
yeah,
it will be that we'll definitely run into more like stuff that we did not anticipate. So that is also one of the reasons I'm doing this. Like we're integrating a real world workload. I mean, performance optimizations are also very important, but in terms of completion, a real world workload is going to give us more, like a lot more corner case to deal with.
Well, yeah, definitely. That's one of the things that we try to do at with the research at UCSD is, we don't just run a simulation or a theoretical, exploration of something. We'll actually try to get, some sort of actual application running and and build something in hardware or whatever. And by doing that, you can really find all of the corner cases and whatnot that you didn't think of earlier.
Yeah, exactly.
You can really shake out a lot of the issues and learn some interesting stuff. So it's really cool to see you guys are doing kind of the same thing.
Yeah, I mean, that's like I was the reason I started the master thesis on this topic is, okay, we have this cool pSpin thing in the group, right? But then what do we like? It's just a simulator, and there's a potential for this to be actual, like to have actual applications running and more people actually playing with this. So that's the core motivation here. Yeah.
Right. Yeah, and I guess that's also one of the things of FPGA versus ASIC, right? With an FPGA, you can actually test this stuff out in hardware without too much difficulty. Versus ASIC, that's a lot of dollar signs and
yeah, exactly,
and a lot of months waiting for a tape out to come back.
And then when it doesn't work, it's a nightmare that you have to stab the chip again.
Yeah, it's like with Corundum, if something doesn't work, okay, let's add an ILA and figure out why, and then rebuild it. And within a couple of days, you figured it out.
Yes, that's true. All right, and another like I wouldn't say question, but actually like just a remark that you probably have seen the issue on the repo about some guy asking for a AXI2 segmented DMA interface conversion. That was me, and
oh yeah. It's at some point something like that would be on the roadmap, but I just everything in Corundum, it's kind of built on an as needed basis. If I need it, I build it. If I don't need it, it doesn't get done. So
yes.
Yeah. So you have put one together, I guess.
I just basically reused the AXI Stream DMA in the module, but there's absolutely no concurrency going on at the moment.
Right,
It's
right,
just
yeah.
like I take a request, I send it out send out the DMA request, I then pop back the response on the data channel or the block, like the write response channel.
So the module put together, it's a master on the internal AXI bus, right?
It's a slave actually.
Oh,
It's a
okay,
slave
okay.
on
So
the
it's
internal.
kind of a bridge module. It accepts an AXI transfer request, and then it
Yes,
performs the corresponding DMA operation. Okay. Yeah, because
exactly.
I'm planning on making both at some point.
Mhm.
But yeah, the issue with the slave side device is that you have to handle like all of the right enables.
Yes,
So the
yes.
byte enables on the right side, and I'm like, okay, I'm not sure how I'm going to deal with that.
I mean,
So
yeah.
I mean, I guess in your case, it's probably relatively constrained to the kind of operations that you're doing, so you can simplify things a little bit. But if you're going to make one that works kind of in general, then
Yes,
that's
yes.
especially for a very wide internal interface. Actually, that's one question. Another question I have is how wide is your internal AXI interconnect there?
That's 512 bits.
Okay, yeah, all right,
Yeah, it's
and then
not.
running
I
at
mean, it's
40
not.
megahertz. So
Well, that gives us how to say, gives us about 10 gigabits of throughput at the moment, which is, I mean, not
it's something.
good, but yeah, it's definitely better than Verilator, for example. Yeah.
Right, yeah.
Yeah, but that's definitely something we can work. I mean, I'm going to work on further because that's what I talked about the synthetic benchmarks. And it's like this is
Right.
something that, yeah, it's a hard benchmark.
Well, actually,
There's no.
another question. If you go back to the block diagram, where are you doing the clock domain conversion? So you're running a lot of logic at 40 megahertz, but where are you switching over between 250 and
Yes,
40?
so I have a backup slide for that, which is like this. So basically, I mean, here, this interface module, like the Mac interface, like that's everything from Corundum ends here, and then the Axie stream interface comes in, right? And then we do Axie stream CDC, and then we go into the matching engine that already runs at 40 megahertz. That is the same with the cluster. So on the entire ingress and egress data path runs at 40 megahertz. I mean, that could potentially run at higher frequency. I haven't tested, but
Okay.
yeah. And then
Yeah, I mean, I guess with this stuff, it's since there's so much interconnection and integration, it's kind of hard to run one module at a different frequency than another module, right? It's like
so
you got to
I'm
figure out
basically
where that
cutting.
CDC is going to
Yeah.
go. So CDCing the data path is relatively easy.
Yeah,
Running the matcher at a higher frequency and then CDCing all the control signals is potentially a lot more complicated.
Exactly. That's difficult. But like on the other side, on the host DMA side, because since I don't really know how to properly CDC the descriptor interface, like the segmented interface, right? So I'm CDCing the Axie masters, I mean the Axie full interface.
Right. Okay. Yeah.
Yeah,
So
and
for
then
that,
yeah.
yeah, I guess the interface for the descriptors and the completions to the DMA engine, that's just basically AXI stream. So there's no problem with putting a FIFO in there. There's no back pressure on the status coming back. So if you put a FIFO, you got to make sure you don't overflow it. Otherwise you'd have a problem.
That's true.
But for the segmented interface, one of the reasons I kind of did things that way is you can just drop down a dual port, dual clock RAM and then run at whatever frequency you want. And then that RAM itself will give you the CDC. I don't take advantage of that in Corundum right now, but it's absolutely possible to do that. And then you can run your internal interface at whatever speed you want. And the fun part about that is you don't need any additional CDC logic at all because the RAM itself gives you the CDC.
Yeah, that's true. Yeah, that's definitely something we can also look in. Maybe I'll look into in the future because what if we want to improve I mean, if I'm going to improve at least try to add some level of concurrency. I mean, I'm not a professional ASIC or say RTL engineer, right? So this is going to fall slower and not be able to run at 250 anymore. And then I will probably move it in and then try to CDC, like basically CDC the descriptors and response, and then use the dual clock RAM interface as you suggested.
Yeah, because that might make more sense just from a resource consumption standpoint, right?
Mhm.
If you can avoid the whole CDC setup on the
Yeah,
AXI
that's
side
true.
and run everything synchronous at 40 megahertz. I mean,
Mhm. Exactly.
40 megahertz is not all that fast compared to 250, but you know, if it works, I guess, yeah.
Yeah,
It
true.
would certainly be nice to see this running faster, but you know, I guess
Yeah,
that's
I mean,
what we call
at the
future
moment,
work.
yeah, I think at the moment, 40 is the reason we're bound at 40 is not really critical path. Critical path, we can probably have like 60 or 70-ish. I mean, 100 would be would need a lot significantly more work. That's the team that designed the core told us. Like what they told us is like
Interesting.
yeah, you need more work to bring it up to 100, but like 50, 60, or even 70 would be definitely possible. But the reason we're running at 40 is because we have significantly, like we have a lot of congestion issues.
Oh, routing congestion issues. Yeah, that's
Yes,
certainly a
because
potential problem.
yeah, because there's like we put in quite a big RAM in here. Actually, we have about 0.5 MB of RAM in the cluster, and
that's shared. So
that is shared across all cores basically. So
right. So I
yeah.
don't know if you've taken a look at the Rosebud paper that Moyne wrote. Have you seen that one at all? I think it
No.
was just published recently.
Yeah.
Yeah. So this was one that, well, I mean, Moyne is the main author on it, but this was kind of built on top of an older version of Corundum, and he
Mhm.
integrated 8 or 16 cores. I think it's, I can't remember how many cores now at the moment. Also on a I think he was also using the VCU 1525 actually, because I picked up several of those for off of eBay a while ago.
Yeah.
But it also runs on the U200. And it took a lot of work to get things operational at 250 megahertz, but the whole data path on those runs at 250, including the cores.
Oh,
So
that's neat.
and they're using the Vex RISC-V cores. So and that one can actually handle traffic into the cores at 200 gigabits a second, right? If you saturate both of the 100 gig ports.
So where is this published at? I mean, I'm going to take a look. It sounds very relevant.
Let me I should actually ask Moyne if he wants to present at one of these things. Let's see. It was just published recently. Let's see here. Is that AS Plus? Might have been AS Plus.
Ooh, okay.
Yeah, I think so. Here we go. I will give you the ACM link here.
In the Zoom
There's
chat.
a chat button.
Yes.
Wink. There we go.
Rosebud. Okay.
Yeah, that guy.
I see. Yeah.
Making it more pleasant. Well, in a relative sense.
All right. This is definitely very.
Moyne lost a lot of hair dealing with partial reconfiguration.
Oh, yeah, that's some nasty stuff right there to like get all the resetting clock and stuff right. It's like just yeah.
Well, it's more in just terms of getting Vivado to build the darn thing without some weird error message or, you know, without some timing failure.
That's true. Yeah.
But yeah, at
And
some point we want to
also-
get that hopefully moved into the Corundum application section as well. So definitely something to take a look at. And that should all be open source as well. Again, old version of Corundum, but so that version doesn't basically Moyne kind of put together the application section before we put together the application section, sort of. So,
okay. So it's not on the same framework, basically. Yeah.
Right. Yeah, there's a lot more modifications, but it should be possible to pull that into the application section. I kept bugging him to do that for this version of the paper, but he didn't have time because it requires a lot of rewriting and retweaking stuff, and with all of the partial reconfiguration shtick, it he didn't think it was worth it, but potentially that can be revisited.
You mean doing a partial reconfiguration block like P block for the application block?
Oh, each core has a P block in Rosebud.
No, I mean P block, yes, but partial reconfiguration region or area. I don't know how this is called.
Yes, each core is its own PR, so you can load each core dynamically.
Oh, yeah, that sounds
In
really,
Rosebud.
really interesting.
Yeah.
Yes. Yeah, I mean, I guess it works for like something like, for example, the Amazon F1 shell, you just replace the entire thing. That's going to work fairly easily. But then if you have that many reconfiguration areas, I can imagine it's going to be pretty hard.
Yeah. I'm gonna see if I can find where they put the code up. Oh, I guess it's, and here's the repo. Yeah, okay. Boink. There you go.
Nice. And then definitely going to take a good look at these because, yeah, there's a lot of stuff that's going to be of good reference, but also, yeah, I mean, generally interesting to us.
Yeah. Yeah. There's probably a lot in there that can be used, although, you know, obviously there are limitations when you're doing stuff on FPGA. So I think each core only has a handful of, you know, memory available and whatnot. And there's
Yes.
definitely a, you know, fair amount of resources taken over with the interconnect. But yeah, I mean, I guess they probably have some figures in the paper showing the reconfiguration or reconfigurable regions.
Okay. Yeah, sure. Do you have any like do you know how long they took for this they worked on this project just as a point of interest? I mean, it's interesting to see how long it took them to pull this off, basically.
It's gone through several cycles of trying to get the darn thing submitted. So
I see.
I think so. It's like I think they actually had basically the whole thing minus, you know, Pegasus and whatnot working like a couple of years ago. But
Okay.
it was hard to get, you know, get it submitted. So there's been a number of, you know, rewrites of the paper and, you know, shopping around to different conferences, and
Yeah.
it's gone through several rounds of revision just to, and then there's been modifications associated with that. But I mean, if you go back as of a couple of years ago, they had the you know, the partial reconfiguration working and all the cores working, and yeah, so I think it didn't take that long to put this together, but I don't know. I guess we also started out with a core that was more amenable to FPGA implementation, right? The VEX RISC-V.
Yeah.
So that might be something to look at for your setup.
All right. Yeah, sure. Going to take more. I mean, we're going to discuss about this really quickly. It's like
Definitely.
loads of people would be interested on this about this on our side as well. Yeah. All right. Cool. Thanks a lot for.
I had a question.
Oh yeah, sure.
Sure.
Yeah, fire away.
Sorry. That works on all hardware platform. This partial reconfiguration.
The which?
The Rosebud stuff. Does it work on every hardware platform, or do you have some limitation?
Every hardware platform. Well, I think it's only been built for a couple of boards. Ostensibly, you could make it work on, you know, any Xilinx FPGA. Intel ones potentially would require a lot more work. Not something we've looked into, but maybe it could be done. It requires a lot of manual screwing around with placement constraints to get the darn thing to work. So we haven't really
but physically speaking, there is no limitation on the you know, on the bitstream itself on the you know, for example, if I want to do that on a Vertex 7, isn't it too old to do that?
Okay, so I think the partial reconfiguration has changed a lot between Vertex 7 and Ultrascale Plus in terms of the capabilities. So I think honestly,
Yeah,
I'm not an expert on partial reconfiguration. I think on Ultrascale Plus it's relatively straightforward.
Okay.
Because you can basically just reload a region, right? You have the partial bit stream for a particular block, you can just load it and it works. But for the other
Okay.
devices, for the older setup, you
Yeah.
actually have 2 bit streams. You have a setup bit stream and a teardown bit stream. So you load the setup bit stream, and then when you want to load a different one, you got to load the setup bits or the teardown bit stream for the bit stream that is currently running to tear it down, and then you load your new one. So it's much more complicated from a logistical standpoint.
And in the meantime, everything stops because you're loading and unloading the whole chip, not a region.
No, this is still
No.
partial, right?
This is still partial.
But it's a more complicated process. So you got to keep track of, okay, which bit stream is currently running in this region, and then we can use the unload bit stream to unload that block and then load the new one. You can't just load a new one blindly, right?
Okay.
And I think that's the case in Ultrascale, and I think that's the case in Vertex 7. And then Vertex 7 is just really slow at this point, so you're not going to run at 250 megahertz with all these cores on a Vertex 7. You could probably run it lower, maybe you could run at 100, I don't know. You definitely have to make some modifications and whatnot for that. And I get also the Vertex 7 parts are not all that big these days, so yeah, if you're going to go that route,
I'm still working with a Sumi board. I have 2 kind of board. I have the Sumi, which is based on the Vertex 7, which is kind of old now, but and I also have a newer, you know, U50, U50, yeah, from Xilinx. That Ultrascale Plus, I think.
At some point, we may have had this thing running on the U50. I can't remember what boards we've run it on.
We tested that. Actually, it works on a
Rosebud.
No, not the Rosebud.
That's what I was referring to. We ported to several different boards, and then I think the ports kind of fell by the wayside because dealing with the partial reconfiguration stuff is such a pain. Yeah, at one point it was running on several different boards, and it might have been running on the U50. I can't remember. I would have to take a look at some of the older code that I have.
For what I understand, the U50 and the other one are kind of similar. Maybe less. The U50 is smaller, but the main architecture is mostly the same.
Right. Yeah. So I think part of the thing that we ran into with running Rosebud on different devices has to do with the layout of the FPGA itself. So it's one of the reasons that we're running on the the VU9P and the U200. This has more to do when you bring partial reconfiguration to bear. If you don't want to do partial reconfiguration, this is less of a problem. But what was the issue? I guess it has to do with the number of URAM columns that the device has, because Rosebud uses the URAMs, at least I think for some of the core memory, like the data memory on the cores is a couple of URAMs and potentially some other stuff. So you need to have a URAM column going through each of the P blocks for the cores. And like if you move to something like a U250, the layout of those columns is different. And I think the SLRs are like a different aspect ratio, and it's like 4 of them instead of 3. So it ends up being I don't think Moyne was able to come up with a solution that worked well on those. Yeah, I can't remember exactly, but yeah, it's like if they had more URAM columns, then it would work. But I guess if you make some trade-offs, you can probably make it work on other boards. It was just, for our purposes.
Yeah, sure.
But yeah, it's it's research, so it's just kind of a proof of concept. Works on a few devices. We got a few cool capabilities. All right. Does anyone else have any questions or comments or anything, either for the P-Spin guys, or on Rosebud, or on some of the buffering stuff I've been banging my head against the wall with in Corundum itself? No? All right. Well, I guess it's been a good meeting. So I guess we'll see you guys in 2 weeks on, what did I say, the 19th? I think so. Yeah. All right, sounds good. And then anybody interested in the switch, I guess we'll probably have a meeting next week, right? The 12th. So we'll talk to you then. And I guess at this point we'll go ahead and adjourn. Unless anyone has any other questions or comments or anything they want to discuss. Going once. Going twice. Nope. All right.
No, thank you.
No.
Sounds good. Talk to you guys later.
Thanks a lot. Bye.
Bye. Thank you.